All right, so let's get started. Um, so welcome to the Deep Learning at Scale training. So in this training, you will basically learn how to effectively deploy deep learning applications to HPC systems. We will be focusing on performance optimization on GPUs, best practices for scaling, and we'll be specifically focused on a scientific application. We will not be covering basics of deep learning today, but you don't need to be an expert, and we will provide appropriate context as and when needed. And we do have hands-on examples for you to run on Perlmutter that would include training on single GPUs, performance analysis and optimization with profiling tools, and then scaling to multi-GPU and multi-node settings. So we are from NERSC, a bunch of researchers and engineers. So we have Wahid, Steve, myself, and Nestor, Andrew, and Benbin are also around to help you out. And we have Josh Romero from NVIDIA, who's on Zoom, who will be looking at some of the performance optimization stuff. So why are we here today? Hopefully, most of you know that deep learning is a powerful tool that's transforming industry and science. But it's training deep learning models is computationally very expensive. For example, training some of the largest language models today takes more than 10 to the 25 compute flops. But training deep learning models is very well suited to HPC systems. And basically, if you're able to effectively use modern HPC systems, then you can greatly accelerate your deep learning workflow. So how do we do that? So the basic strategy is you start with an appropriate model architecture, which trains on a single CPU or a single GPU. And then you would go and optimize the single GPU performance. So you would use performance analysis tools. You would make sure that you're tuned and optimize your data pipeline. And basically, you have to make sure that you're utilizing the underlying hardware as effectively as possible. So in our case, these are NVIDIA GPUs. And then as your problem size gets bigger, you would distribute your training across multiple chips. So you would do multi-GPU and multi-node training using something called data parallelism. We want to make sure you're using best practices for large-scale training and convergence of your models. And also, it's always a good idea to make sure you're using the best optimized libraries as possible. And then if you're really going into much bigger problems, like, for example, like in large language models, then you would want to think about advanced parallelization strategies, and these will include model and hybrid parallelism. You have to think about the design considerations for this, how do we actually implement them, and analyze where your performance bottlenecks will be coming. And that's what we're going to be doing today and tomorrow. We will be using Perlmutter. Hopefully everyone's familiar with what Perlmutter is. It's NERSC's Vision Science HPC Center. We have more than 7,000 A100 GPUs. I think Steve already went through this, but if you're not a NERSC user, you should be able to request training accounts for the duration of this tutorial. We do have compute reservations set up for the training event, so up to about 1,000 GPUs. All the examples that you will be running and we'll be showing you use these reservations by default, but if you want to do stuff later on after the training, you can just turn off the reservation flag and you should be able to still submit jobs to Perlmutter. We do recommend that you use the Jupyter service at NERSC, and we'll once again keep flashing that slide on how to get started with Perlmutter, because it's pure web browser based and you can kind of edit and browse your files there itself. But if you prefer, you can always SSH and use Vim or something like that also. Completely fine. It's up to you. So this is the agenda for the full training event. So today, we would actually spend the first hour just introducing the problem that we're working on and getting everyone situated with Perlmutter. Then we'll take a short break and then we'll hand it over to Josh, who's going to be talking about performance on a single GPU, and then we have a hands-on section for that to profile and optimize single GPU training. We do have some buffer space after that in case things overflow or anyone has questions or discussions. And then tomorrow we'll be doing scaling this model to multiple GPUs, first using data parallelism. There's going to be an associated hands-on for that with break, and then we'll finally do scaling with model parallelism, and there'll be a hands-on for that as well. Okay, I think this is already presented, but essentially a one-stop link for getting all material is our GitHub repository. links to the slides, instruction code, links to data downloads in case you want to run things outside of Perlmutter, it's also possible. Those links exist in the GitHub repository. Okay, so just for like 20 minutes, I'm going to introduce the science application we're going to be working on. Give you guys a very high-level overview of what we're using the deep learning model for and what is the end use case science application. I won't be going into a lot of details, but it's good to have at least a broad idea of what we're trying to solve. We will be focusing on weather forecasting using deep neural networks. So weather forecasting essentially amounts to modeling atmospheric physics over the entire Earth. It's an extremely complicated phenomenon. It has a wide range of physical processes that occur over many spatial temporal scales. Traditional models are numerical solvers that solve hundreds of partial differential equations and also assimilate those equations with observations continuously. So traditional models are numerical weather prediction models. They run on dedicated machines with many compute nodes running these physical models plus data simulations 24/7. This is very expensive. And all this expense is amplified because weather is inherently a chaotic system, which means that any small perturbations that you have in today's weather can grow in time and become a little unpredictable. So the general strategy of how this is dealt with is people build many forecasts. So they build an ensemble of forecasts to quantify the uncertainty in your predictions. And this can be very critical, especially for things like extreme weather, like heat waves, precipitation events, hurricanes, where it's really important for you to model the tails of the probability distribution really well. But what this means that all that cost of generating a single forecast is now amplified because you have to generate multiple forecasts all the time. Today, data-driven models have shown a lot of success. They did start off pretty small back in 2018, where kind of forecasting the weather on a 6-degree resolution. What that means is if I kind of project the weather state onto a 2D grid, that only looks like about 60 by 30 pixels, so not that big. Over the years, we've gone all the way to like 16,000 pixels, and in 2022, reached 64,000 pixels, and finally 1 million pixels, which translates to like a 0.25-degree resolution. And this is the resolution at which operational weather forecasts happen. So data-driven models have reached that resolution back in 2022. And since then, there's been like an explosion in AI models, both from research labs and academia, as well as industry, including like NVIDIA, Google, Microsoft, etc., building better and better models. And essentially today, deep learning models can outperform the forecast skill of a traditional numerical weather prediction model. And as of 1 week ago, the European Weather Forecasting Center has made its AI model fully operational. So a lot of these models are based on the transformer architecture. And essentially, they require many days or weeks of training on multiple GPUs or TPUs. So Google's models runs on TPUs. And for today, we will be focusing on this example. The data set we're going to be using is called ERA5. It's an open source data set from the European Center for Weather Forecasting. It is a reanalysis data set. What that means is that they've kind of run a physical model, a PDE solver, and then assimilated that with observations continuously. And have generated the weather state over the past 40 years on a 25-kilometer resolution. 25-kilometer is the million pixel resolution that I was talking about. And if you just want to think about what that data set looks like, it looks something like T class, V class 720 by 1440, where T is your number of time steps. So you have 40 years of data. It comes with an hourly resolution. So if you actually calculate, that's almost like 350,000 samples. You have that for V different variables. So in weather, you're forecasting multiple different atmospheric states, like temperature, pressure, humidity at different vertical levels over the Earth. 720 by 1440 is your spatial resolution. Even though atmospheric physics happens on a sphere, it's usually projected onto a lat-long grid that's essentially a rectangular grid. So these are like some snapshots of some weather variables, like water vapor, for the geopotential height, and wind velocities over the entire Earth. V is typically all the hundreds of variables that you are forecasting. And LFI is often thought to be the best available estimate of the Earth's atmospheric state over the past many decades. So what is the weather forecasting problem formulation? You're given your atmospheric state today at time t. Atmospheric state means three different variables over 720 by 1440 is your spatial resolution. You want to predict the atmospheric state at t plus delta t given this initial condition. That's the weather forecasting problem. And then in order to predict the weather in future time steps, you just do this auto-regressively where you take the prediction at t plus delta t, feed it back into your model to get the prediction at t plus 2 delta t. You keep doing that again and again until you hit like 2 weeks. And that's how you get the weather forecast for the next 2 weeks. But this is the problem that we're going to be solving today. We're going to be using the transformer model architecture. So we did send an email to everybody on getting started with model architectures, but I'm still going to give a high-level overview of what the transformer model is, what it's trying to do, and how we are going to be using it for this problem. So from a very high level, what the transformer model does is it takes a sequence of tokens as input and predicts a sequence of tokens as the output. The transformer model itself is comprised of two main computational engines. It's called self-attention and MLP. MLP is multi-layer perceptron, also called a feed-forward network. And this is just repeated many, many times, and then the output is a sequence of tokens. So if you think about, let's say, a large language model, they basically use transformers. The sequence of tokens is essentially just a sequence of words, like the prompt that you type into ChatGPT, for example. Goes to the transformer. The transformer predicts the next token in that sentence, and then this goes back, and it keeps auto-regressively happening until you generate the full response. So this is what happens underneath the hood when you, for example, go type a question on something like ChatGPT. For weather, nothing changes in the architecture except your sequence of tokens now needs to represent your atmospheric state over the entire globe and for V different variables. And then the output is going to be the atmospheric state again, but at time t plus delta t. So that's the only difference. In order to do this, we're going to be using a model called Vision Transformer. And what it does is it tells you how to create the sequence of tokens. So it's very simple. All you do is take that image that you have, you create patches. So you grid it up into different patches. And that represents your sequence of tokens. So tokens is now just embedded patches. That goes into your transformer. And you predict a sequence of tokens in the output, again, sequence of patches. And all you do is assemble it back into the image. And this is, once again, the atmospheric state at t plus delta t. A different way of thinking about it is just in terms of tensor shapes. So once again, you had as input 720 by 1440. That's the image size. You have V different variables. All you do is create patches. So you reshape that into V times P squared cross L. So P is your patch size. So I'm kind of assuming it's a square patch. L is often called a sequence length. In this case, it just represents the number of patches that you have over your entire image. And what you do is you kind of embed this into a higher dimensional space. E is typically called the embedding dimension of the transformer. This is very similar to most machine learning models where you're trying to learn your approximated function on a high dimensional space. So this L cross E tensor goes into the transformer. It predicts an L cross E tensor again, and you just reverse this process to get back the final image. So this is what we're going to be doing in the tutorial, and we're going to be optimizing the performance of that model and then parallelizing it using data and model parallelism. The last thing I want to say is that just to go one level deeper and explain what self-attention and MLP are. Once again, a transformer is just repeated blocks of self-attention and MLP. And if you have your input tensor, which is L cross C, once again, L is sequence length, E is embedding dimension. You typically have a batch of these tensors because you have a data set over which you're optimizing. That goes into self-attention. The output of self-attention is still a tensor of that same shape. That goes into MLP. And the output of the MLP is once again a tensor of the same shape. This is a very nice property of transformers. Like unlike convolutional models, there's no like downsampling, upsampling. Everything is like very, very nicely load balanced. And if you think about what the MLP is. It's also called a channel mixing MLP because all it does is it learns relationships in the embedding dimension. So you do a linear transform into a higher dimensional space, E to 4E, apply a nonlinear activation function, and bring it back to E. That's what the channel mixing MLP does. The self-attention is a little bit more involved. Here you're modeling relationships in the sequence length dimension, which is L, which represents our spatial dimension once again. So sequence length is just total number of patches. And what the self-attention does is you can kind of think of it in like three steps. This comes from language models where you take your input and you project it into what's called as query key value tensors using a linear projection. QKV, each of these tensors are also of the same shape, so it still looks like a batch times sequence length times embedding dimension, all good. And then you compute what's called as a similarity matrix, also known as an attention matrix. This is a matrix of size L by L. So it's sequence length by sequence length. And what it's trying to do is it's trying to model the relationship of every token in your input to every other token. So for example, the ij entry of this attention matrix is telling me how much token I is related to token j. If that value is really high, those two patches in my image are related. If it's very low, they're probably unrelated. In deep learning, you have nonlinearity, so it's softmax in this case. It converts those into probability scores. You do a final projection with the values tensors, and then you get back your input tensor shape again, batch, sequence length, and back dimension. There's one caveat here that you can do this with multiple different heads called multi-head attention, but for the purposes of today, it's not super important. I've linked the vision transformer paper here for more details, but this high-level overview should be enough because we are more interested in performance optimization today. Last thing is that all our hands-on is going to be in PyTorch. You can certainly do all of this in TensorFlow and Keras. They all have equivalent functions that you can use. PyTorch is what we recommend because it's very easy to integrate with other Python code, similar to Keras, and it has good performance and distributed training with support for MPI and Nickel. For the data set, we're actually going to be using a downsampled version of L5. So it's going to be at a 50-kilometer resolution, not 25 kilometers. That's because you want to make sure that when you actually submit jobs, you can actually see the job training to some sort of convergence and you see some good results. Because these are like actual real applications, and usually it takes many, many days to train a model to convergence. So we will be focusing on training today, training performance, but inference is pretty similar to training performance. You can easily extrapolate. Okay, so before we get into like logistics of getting started on full model, are there any questions?
You're online, feel free to.
Yeah, if you're online, feel free to unmute.
So I have a question. I'm confused about the sequence length is the number of small little images within an image, or it's the number of images?
It's the number of patches. So you take this big image. If my patch size was 1, like just a single pixel, my sequence length is actually 720 times 1440. So my patch size was, let's say, 8 by 8, 720 by 8 times 1440 by 8. So it's just the number of patches. The more patches that you have, the complexity of the operation starts to radically explode.
But how many images do we have before you get patches?
You have V different images. That's number of channels that represents different variables like temperature, pressure, things like that.
So V is the number of images.
Yep.
L is the number of small patches.
Exactly, right.